Okay, great. So, hi everyone. Welcome at our weekly TCS seminar at Jagiellonian. Today, our speaker is Jędrzej Hodor. He's a master's student within our group. And Jędrzej will present us an overview of results and I think also research ideas within the posset dimension project. This one we are carrying on already for some time, and we made some progress this year with help of Jędrzej, with help of Michał Seweryn, but also because we had a very distinguished guest, Tom Trotter, who is also here in the audience, was with us for 6 months, and I understand that this talk is a little bit of like a report. What did happen? So, Jędrzej, the screen is yours.
Okay, so I think the introduction is already covered, so let us just start. And the first thing to explain is what is a posset. So a posset usually is drawn as some dots and some arrows, and this is some example of a posset. We have yellow below red below blue below purple, and also we remember that posets are transitive structures, so yellow is also below blue and purple, and so on. And we remember that posets do not contain cycles, and this one doesn't, so it's fine. Yeah, but this is some drawing. Let's maybe formalize it a little bit. So to understand what is okay. So these are transitive edges, which I mentioned, and to formalize what a drawing is, we need a notion of covers. So x less than y is a cover in posset if there is no z which we can plug in the middle. So for example, yellow to red is a cover because there is nothing in the middle, but those gray transitive edges are not covers. And because they are transitive edges and they can be inferred from the picture only of covers, we usually don't draw them. So knowing what a cover is, we can define a cover graph, which is just a graph of covers. It can be considered as a directed graph or undirected, and usually I will mix these two. Okay, but cover graph is just a graph. So usually when you see posets, they are drawn in a way such that all comparabilities go up, and this is what we call a diagram. So a diagram of a given posset is a drawing of the cover graph of this posset with all edges going up. So for example, this one is a diagram because if we have an arrow, it goes up. By up, we just mean up in a plane. Okay, and so this is a very simple posset. Let us show some more complicated ones. So these are some posets, and these are diagram of these posets. So in each of those drawings, if I have a black line, then it means that actually I have an arrow from what is below to what is above. So for example, this red is below this blue, and this blue is below this purple, and so on. Okay, and now we go back to the title of the talk, to the topic. It should be about planar posets. So what does it mean that a posset is planar? In graph theory, it is very intuitive and obvious what planar means, but in posets it's a little bit more subtle. So we have two notions of planarity because we have these diagrams and cover graph. They induce two natural notions. So we say that a posset is planar. This is more classical notion if there exists a plane diagram. So for example, this one is planar because this is planar, no edges are crossing. Yes, by plane I mean no edge crossings. So there are no edge crossings. And cover planar, I mean a posset for which there exists a plane drawing of the cover graph. So in such a drawing, there might be some edges which go down, not necessarily up. So let us consider some examples. These are examples which I want to consider. So first of all, Okay. One more thing. Planar obviously implies cover planar because the diagram is a specific drawing of the cover graph. Okay, and now let us move on to this first example. So I can redraw this poset, still preserving being a diagram, so still having all edges going up, in such a way that no two edges cross. So I moved this 3 here, I moved this 1 here, and I moved this 2 a little bit down, and I get a planar drawing with all edges going up of the same poset. Yes, still, for example, still 2 is not comparable with this middle blue. This is preserved. So plane diagram means planar poset. Now let us move on to the second one. We can almost do the same, but I attached this minimal yellow and maximal purple, and they are not helping. For this purple, for example, it can be attached also to this lower drawing, but this yellow one, it cannot be attached from below to 3 and 1. So it has to be in the middle, and to have yellow below this red middle guy, I have to draw an edge which goes down. Yes, this is not a proof. This is I mean, this is not a proof that I cannot do this, but this is some intuition that sometimes allowing edges going down gives us some more power. So this poset is only cover planar because I was able to draw a cover graph, the cover graph of this poset in a plane drawing. Yes. Okay, and the last one is actually K33 seen as a graph, so I can just see cover graph as an undirected graph. It's K33, so there is no way to draw it in a planar way. Okay, so this is what we mean by planar posets. We have those two notions, planar posets and cover planar posets, and we will work with both of them. So the thing is to remember is that in one of them, all edges go up, and in the second one, some edges might not go up. Okay, so this was about planarity. Now, what about dimensions? So the second part of our title. Dimension is some measure of complexity of a poset, and first I will define it in a classic way, and then in some later slides I will give some more intuition on how one can compute this dimension or bound it at least. Okay, so let's us fix some poset P, and we need a notion of linear extensions. So L, which is an order, partial order on the same ground set, is a linear extension if, first of all, it's total order. So all pairs of elements can be set which one is smaller and which one is larger, and it preserves P. So if X is less or equal Y in P, then it's also less or equal Y in L. Okay, so let us consider some examples. First, let me label vertices in this poset, and next let me add some edges which because 2 and 5, for example, were incomparable in this previous picture. Yes, now 2 and 5, I cannot say which one is larger, but if I add those pink arrows, then I can say that 5 is less or equal than 2, and I can do the same for every pair which was not comparable, and this is a linear extension which I obtained. So 1 is the smallest, then I have 5, 2, 3, 6, 4. Yeah, and this is a linear extension. Now I can do it in some other way. For example, I add these edges, and now 2 and 5 again are comparable because from 2 to 5 I can get through there. And in some maybe even stranger way, 6 can be the minimal element, even though it's drawn very high in this picture, and so on. Okay, and an important observation about linear extension is that if we treating them as binary relations, if we intersect all of them, then we retrieve whole poset. Yes, this is a simple fact to be proved, but it's true. So we can ask, what is the minimal number of these extensions which suffices to retrieve the whole structure of P? And this is what the notion of dimension is about. So dimension is just the minimal number of linear extensions such that intersected they gives us P. And as I said, I will talk later a little bit more how one can treat this notion in a more practical, maybe with a more practical approach. Okay, so observation. This inclusion is always true because if x was, let's recall, p than y, then it's also so the comparabilities are preserved, and this shows this gives us one inclusion. So this indicates that the only thing which we care about in this linear extension are incomparable pairs. And we need to somehow reverse these incomparable pairs such that they do not appear in this intersection. Yes, and by incomparable pairs, I of course mean two elements which are not comparable. Okay, so let's move on. When we talk about dimension, we should show some example of a poset which has large dimension. Yes, just to show that this notion makes sense. And standard example is a standard example which is shown in this as an illustration. And this is a standard example S5. So I have 5 minimal elements, 5 maximal elements, and each A is below all B's except the one with the same index. So for example, A3 is below B1, B2, B4, B5, but not B3. And dimension of Sn is n. I listed linear extensions which show that dimension of this particular standard example is at most 5. So I have 5 linear extensions, so I can realize this poset with 5 extensions, but maybe I can do better. It can be proved that I cannot, but let's look at them for a moment. So in each of them, the middle thing is that AI is reversed with BI. So AI-BI is an incomparable pair. We don't have a comparability here, and they are reversed. But note that, okay, if I reverse A3, B3, so A3 is above B3, then note that all other B's has to be above A3, and all other A's has to be below B3. So this actually is a proof that this is exactly n, because I have to reverse those pairs, yes, to get that this intersection is P, but I can do it only in such a way. Yes, and maybe first I should tell that it really realizes this poset. So okay, if we look at two A's, they are incomparable. One of them in some extension is the largest A. For example, if I take A3, A5, then A3 is the largest here, so it's above A5, and A5 is the largest here, so it's above A3. So A3, A5 is not something in a poset, it's an incomparable pair. And one can do the same for B's, and yes, and that's it. Okay, so next we define another notion of measuring complexity of a poset. So this is standard example number, and this is a maximal size of a standard example, which is a subset of P. In the world of poset, we always mean induced. So if I have an incomparability, then it should be an incomparability also in this P. Yes. Because otherwise we don't have this. Yes. Yes, we don't have monotonicity of the dimension, and we like monotonicity of the dimension. Okay, so by monotonicity of the dimension, we have standard example number bounded from above by dimension. Okay, and now I already made some remarks about some analogical phenomenon between posets and graphs, and now I will do more of them because in some sense, dimension is analogous to the chromatic number. In some sense, standard example is analogous to the complete graph. In some sense, standard example number is analogous to the clique number. And yeah, to justify this, we have dimension of Sn n, and also we have chromatic number of Kn n. So this is the same, and also we have this inequality, which is the same. So so this is why this analogy can be considered. And in graph theory, the notion of chi-boundedness is considered. So chi-boundedness asks if you can bound chromatic number by a function of clique number. And in posets, we consider the same thing, I mean, analogous thing. So it's dim boundedness. We ask if dimension can be bounded by function of standard example, yes? And in a philosophical way, it is just asking for reasons why dimension or chromatic number is large. And if this reason is clique number or standard example number. Okay, so in the graph theory, we have some triangle-free graphs with large chromatic number, and also in posets, we have some small standard example free posets with large dimension. And so this shows that the answer for dim boundedness in general is no. So there is no such function. But of course, we can ask for dim boundedness in some particular classes of posets. And this is what we are going to do. But first let me maybe show this example of an S4 free poset with large dimension. So we define something called incidence posets, and this is a poset where for a given graph, and in this context, we only use cliques. So for a clique, and here it's K5. We put vertices as minimal elements and edges as maximal elements of this graph, so K5. And we connect each vertex to each edge which contains this vertex. And note that these maximal elements have degree 2. So, and in standard example world, this degree of maximal elements is n-1, so 4 minus 1 is 3, so S4 is not possible here. And one can prove, but this is a different story, that dimension of pkn is omega of double logarithm of n, so it's in particular unbounded. Also, if we don't want to have S3, there are S2 free posets even, which are interval orders, which also have this property of having large dimension. But this is just a remark. And I said that this problem of dim boundedness can be considered in particular classes of posets, and it's known for posets where the cover graph has bounded triwit, for example. And yes, this is also quite a new result. But we care about the planar case, and in the graph theory, there is nothing interesting in the planar case in sense of chi-boundedness. So clique number is bounded by 4, chromatic number is, we know that it's bounded by 4, but for very easily we can get that it's bounded by some constant. So there's nothing to do here. But in posets, this is much more complicated, and this is actually what we want to talk about today. Okay, so this was introduction of this notion of dim boundedness and dimension standard example. This is going to be important. Okay, next we ask a natural question. Do cover planar or planar posets have bounded dimension? And I already introduced the notion of dim boundedness, so probably the answer for this is no, and of course it's no in both cases. And let me give examples which show that really this answer is no. So the first one, okay, this is just a recollection of what standard example is, and that dimension of standard example is n. And now this is the first example. It was given by Trotter in 1978. This usually we call it the wheel, and this is a cover planar poset, so it has a planar cover graph. And the most interesting fact about this poset is that it's cover planar and that we have standard example in this poset. So how do we have the standard example? Reds are reds in a standard example and blues are blue in the standard example, so like here. And let me tell a little bit more. So take A1, and we need to show that A1 is below all B's except for B1. Okay, so I didn't underline this. Maybe it's important. All comparabilities go in, like those arrows here. So this is a cover graph. I didn't draw arrows because then the picture gets messy. But you should remember that all comparabilities goes in. So for example, this element is under this element. It's under this element. It's like spirals which are going in. Okay, and that's I will illustrate it also a little bit more in a moment. So A1 is under B6 just by taking this chain. If we turn here, then we get under B5. Then if we turn here, we get under B4. If we turn here, we get under B3. And if we don't turn but follow the spiral from the beginning, we get under B2. And it's not that hard to see that this is the only B's we can be below, because those are not these edges are not going in the right direction, and I cannot go any further, so I am incomparable with B1. And the same can be checked for each A and B. But yeah, this picture is symmetric, so I think maybe even I proved this. Okay, but let's move on. So the next, so cover planar posets don't have bounded dimension. And now the second example. So now we want a planar diagram. So now all edges go up. And we have plane diagram of Kelly 6. So 6 again, 6. Again, we have standard example, a subposet of Kelly n, and the number is just a number. The number here is a number, the same number as here. Yes? So how large standard example is inside this Kelly. And again, reds and blues constitute standard example. And again, we have to check that for each red, we are under all B's except a B with the same index. So I picked A3 to illustrate this. A3 is under B1. We can go this direction. Now, if we turn here, then A3 is under B2. There's no other B's that we can reach going from the left. So now let's go from the right. We get B4. We get B5 and we get B6. Yes, and we are not under B3. Yes, so this example is quite clever, and to understand it deep, you should look at it for a moment longer. But what it shows that really we have standard example, a subposet of this Kelly n, and this means that planar posets also don't have bounded dimension. Okay. So the natural question now, we know that planar cover planar posets don't have bounded dimension, and we also don't know that they may consist of large standard examples. So it's natural to ask about this dim boundedness problem. So our main question, so this is the main question of this area, is, are cover planar or planar posets dim bounded? And this question is quite old. It dates back to even to the 80s. One can say that half of it is already solved. The other half is still open, but I will get to it in a moment. Oh, and this is just to recall what dim boundedness meant. So dimension was analogical to chromatic number. Standard example was analogical to clique number. And dimension, we ask if dimension is bounded by some function of standard example. Okay, so this is about dimension of planar posets is unbounded, and we have these two examples which are very important. And I think we can move on. So here I just repeated these two constructions, our main question, and an observation that this question is hard in general. So maybe there are some intermediate steps we can take, and we can prove something less, because at first glance it's not clear what could be these intermediate steps. What can we relax to make this problem easier? And I will try to explain you what are natural intermediate steps in some poset-like sense. So to understand this, we need unfoldings, and I will define what unfolding is and why it's important. So we start with we have a poset, and we start with some minimal element. We call it x0 here, and we draw all elements which are in the upset of x0. What is an upset? These are all elements which are above x0. So for example, it's not given that they are above by a cover, but they might be above by a transitive edge, like this element. But those are, yeah, this is the upset, and this is our first bubble. Then we take all elements in this blue bubble, and we take downset of this bubble. Yes, so all elements which are below these elements, and we get a red bubble. Now we forgot about the previous stuff. Yes, so we don't want to repeat anything. We look for new elements which are in upset of the red thing, and there are some elements. Yes, this is next blue bubble, and we can go on with this for arbitrarily long time. But this is called an unfolding. And what's nice about unfolding? It's that it behaves nice with the dimension. What do I mean by behaving nice with the dimension? It means that one of these pairs of these bubbles, neighboring pairs, carries large dimension. By carries, I mean that at least half of the dimension is realized in this subposet, which is these two bubbles. This is what this lemma says. Yes, so there exists by p prime, I mean just a pair which it can be tilted this way or tilted the other way, but let's assume for simplicity that it tilted this way, and its dimension times 2 is at least dimension of p. Yes, so it carries a lot of dimension. Yeah, much dimension, let's say. Okay, and what does it help? So starting with only blue, only red, and forgetting about everything else is not the best idea, because then everything can happen inside. But remember that this blue didn't came from the thin air. Yes, it came from the previous red. So we can take all this stuff which is before this blue and contract it to one vertex. Okay, and by contract I just mean as a minor or something. With a fixed drawing, we contract it in a planar sense. Also, we can forget about everything which is after this heavy pair, because it doesn't give us much. I mean, we have enough information in this pair. Okay, but this thing which I've done, so contracting, works only for cover planar case. Because by contracting, I could have done some things like that. Yes, so some of the edges might have to go up and then down, or down and then wiggle somewhere, and it might be very complicated. So I cannot contract things in a planar diagram and preserve comparabilities. Yes, because some edges may change to not be diagram edges, to be cover graph edges. Okay, so let me discuss this. What happens in planar case? So in planar case, I don't get a single minimal element which is between the whole blue part. I get a minimal element which has zigzag paths to all minimal elements of blues. By a zigzag path, I mean a path which can go up, then down, then up, then down, up, down, and so on. Yes, and what does it give us? So okay, having a unique minimal element under the half of our poset is very nice, but this one is also nice. This gives us something which is called accessible from below. So every minimal element is accessible from below in the sense that I can go from it down and then walk with in some zigzag manner and leave the drawing, so get to some infinity, some outer face. Yes, and this also makes some things easier. But let's move back to the question which I started with. So what are these intermediate steps? So obviously easier case is when this red is empty. So let's forget about the red and let's for a moment focus on the case where the red is empty. Then what happens? So in this cover graph situation, we have a zero. So by a zero in a poset, I mean an element which is minimal in general, in global sense. So it's under every other element in the poset. Yes. So this x naught prime is really a zero, and it's a minimal element. And in the planar case, this blue poset is accessible from below, in the sense which I discussed a moment ago. Yes, so this case with empty red is different in both settings, but in both settings it gives us a very valuable information, that in this one that all elements are above one given element, and in this one that all elements are accessible from below. Okay, and all this discussion leads us to the following table. We have a planar case, cover planar case, and we have these two assumptions. So so accessible from below in planar is analogous to having zero in cover planar. So I could left out this cell, but it's also solved. So why not? So zero in the planar case is something else. It's not following this line of reasoning, but it's still interesting. And yes, and I think we are ready to discuss what are the results in each of these cells. So let's start with the simplest one. If we have a planar diagram and we have a zero, so then a unique minimal element, then some long time ago it was proved that dimension is bounded by 3 simply. So there is no such examples, and dimension is bounded by 3, and I will actually prove this for you. Okay, next one is this accessibility from below in the planar case, and this is much less trivial. We have also bounded dimension due to this group of authors some time ago, but I'm not going to discuss this result because it's not that connected with the other ones. But it's maybe important to underline that these results with empty red virtually should be used in the general proofs. Yes, we have to solve these to get a general case. So in this proof, for example, we use this one as a black box, and probably yeah. Okay, so let me move on. The next one is when we assume that there is zero in a cover planar case. Note that zero in accessible from below in a planar cover case, which should be clear by now, is the same thing. And recently, Heather Smith-Blake, Piotr Micek, and Tom Trotter proved that this is really dim bounded. And with a very nice function. So this is a linear function with a very small constant, and I will try to show you an idea which stands behind this proof. Next, okay, and now I have a side note. So one can attach zero to this Trotter's wheel. So this shows that all of this makes sense. Yes, the dimension here is not bounded because I can there is a poset which has planar cover graph and a 0 and unbounded dimension. Yes, so here question about dim boundedness is a fine question. It's not like this dimension is bounded by 13 or something. Okay, next result is the most recent one. We proved with Piotr Micek, Michał Seweryn, and Tom Trotter like a month ago or something that in the planar case with no restrictions, we have dim boundedness by 128 standard example plus some constant. We are still working on making this constant smaller, and the C is about, it's not that large. It's just this result is not yet written, so some details need to be filled in. And the last one, the most general, is still open, and yeah, and so I leave it. But there is some work going on here, and also there are some more intermediate steps between these two cells, and some of them are already solved. So it's not like it's not that we don't know what to do. It just seems harder. Okay, so this is about what are intermediate steps and what are the results, the most recent ones. And now let me move on to the proofs. Oh no, sorry. Before the proofs, I have a slide about dimension. So I announced that I will tell you a little bit how to approach dimension in a more practical way. So this is a definition that I gave you at the beginning. So it's just a minimal number of linear extensions to be intersected to retrieve P. But now let's do it in some other way. Let me define inc of P as all incomparable pairs in P, so such that A is incomparable to B. And let me show you an example. So I have some E, which is a subset of incomparable pairs, and those are these red-blue pairs. Red are A's, blues are B's, and I take some linear extension. So black elements in this extension are the sum elements, and I have all of these reds, blues in this extension. Okay, and now note that each red is above corresponding blue. So for example, this light red is above light blue. Okay, now it's easier. This red is above this blue, this red is above blue, red above blue. So this means that I reversed all my pairs. So L reverses I. And if such extension exists, then I is reversible. And having this notion, one can define dimension in an equivalent way to be the minimal size of a partition of incomparable pairs into reversible sets. I will not prove that it's the same, but it's not that hard, and maybe it's a good exercise if someone have never seen this. So incomparable pairs are divided into I1, I2 up to ID. We want to minimize this division, and each II is reversible. Okay, now, but okay, this reversibility notion is still quite abstract. So there is a tool which allows us to cope with reversibility better. So I is reversible if and only if it does not contain a strict alternating cycle. And what is a strict alternating cycle? It is such a structure. So I have A1, B1, A2, B2. I have pairs from I. So A1 and B1 is from I, A4, B4 is from I, and so on. And I have comparabilities like this one, and that's why it's called cycle. And I will not prove this. I will just show an intuition why one of the directions is true. So suppose that we have a strict alternating cycle in I, and suppose that it's reversible. Yes. So this is one of the directions. Now I have a linear extension which reverses this cycle. But okay, if it reverses it, then A1 is above B1. Yes, this first pair. But B1 is above A5 in a poset, so it has to be preserved. But A5, B5 is reversed, so B5 is lower. But B5 is above A4, so we have this, and so on. So A4, B4, B4, A3, yes, we go this way. A3, B3 is reversed, B3, A2 in a poset, A2, B2 reversed. But now we have B2, A1, and this is not right. This is wrong. Yes, because B2 should be above A1 and it's already below, so a contradiction. Yes, so this shows that one of the direction is satisfied. The other one is not very much harder, but I think this one illustrates why this alternating cycles are interesting. Yes, and also by strict we mean that there are no other comparabilities besides these ones which are drawn. Okay, so this is about practical approach to dimension, and we will do it a lot. So now let's move on to the proofs, and let me start with this simple thing about planar posets with 0. So I assume that the poset is planar, meaning have planar diagram, that it has a 0, and I want to prove that dimension is bounded by 3, and this is due to Trotter 77. Yes, so first of all, we define the leftmost path to x. So we have this 0, x0, which is under all elements, and we take some x, and now I check all edges which exceed x0, and through which I can reach x, and I take the leftmost one. Now I do the same. So I check all edges through which I can reach x, and I take the leftmost one, and so on. And this gives me a path. And I will call this path the leftmost path to x. So very, very natural notion. Of course, I can do the same with the rightmost path to x. And now having this, I can divide my incomparable pairs into types. And what are these types? So first type is a left pair. I have AB incomparable pair, and this is a left pair. What does it mean? So it means that the leftmost path to A is left of the leftmost path to B, and the rightmost path to A is left of the rightmost path to B. Yes, as in this picture. I mean, and of course, it's very natural. What does it mean that a path is left to other path? When they split, one go left, other go right, and the one which goes left is the left path. Yes, and if they are extreme paths, they cannot meet again, because then we can alter them to get more extreme path. Yes, okay, so left meaning that so by picture meaning that A is left to B. Now this is right by picture meaning that A is right to B, but it's defined with using those leftmost rightmost paths. And we also have outside inside where because this was left, this was right, and now we have left, right, left. But the name should speak for itself. Here A is outside, and here A is inside. Okay, and now this here in the corner we have a recap how to bound this dimension. So we have those strict alternating cycles. If there are none, then a set is reversible. And we want to divide incomparable pairs into some small number of reversible sets. So we divide it into three sets. Of course, I said that it was partition, but they may overlap. It's not important if they overlap. So for example, here they overlap. I1, I2 have some common elements, but it's not important. And I1 is left pairs and outside pairs, I2 is right pairs and outside pairs, and I3 is inside pairs. And note that, okay, left, right are symmetric, but outside, inside are not symmetric. And why is that? So this is because here A is lower than B, and this is a natural behavior. So I can put here an edge, and this is fine. Yes, this is a normal comparability. But here, A is above B. So I cannot put edge here because this is a planar diagram. So if I put an edge here, then B is below A, not the other way around. And we have this AB, this order, yes? That's so, yeah, this is just a note why these two are not symmetric. This might be confusing at first. Okay, so let me prove that each of these sets is reversible. So we will start with I1. If it's not reversible, this means that it contains a strict alternating cycle. of some length, which we don't know. What is this length? Okay. So I start with some BI, and I want to argue that AI minus 1 is inside a region which is is bounded by the leftmost and the rightmost path to BI. Yes, so BI is an element here, and AI minus 1 is an element here, which is below BI. Okay, but this if it's outside, then I have, first of all, X naught is under AI minus 1, and second, AI minus 1 is below BI. But this means that I can take this path to be more to the right than this path, which was supposed to be the rightmost. And also, if this element is on the left side, then I can do the same with the leftmost path. If it's above, then there is no way that it's comparable in the right way with BI. So this shows that this element is actually inside. And this shows that if I go from BI to AI minus 1, we stay in the region. Yes, so this AI minus 1 stays in the region. Okay. Now, now recall that we are in the lefts plus outsides. And what does it mean? It means that the leftmost path to A is left of the leftmost path to B. Yes, the same here. Leftmost path to A is left to the leftmost path to B. So this means that BI minus 1 is right of AI minus 1, not meaning the leftmost path to BI minus 1. Yes, so we have this movement right. But this means that, okay, we knew that this whole thing, this AI minus 1 is inside this region, and BI minus 1 is right of this path, because it's right of this path, and this path is right of this path by transitivity. Then this means that BI to BI minus 1 in some sense moves right, but this cannot cycle. Yes, because this is a cycle, so I did it for every I, and this cannot cycle. Yes, that's why that's maybe some justification why this thing is called alternating cycle. Okay, so this shows that I1 is reversible. Now I2 is by symmetry, so this is exactly the same argument, but replace every time I set left with right and right with left. And about inside, so this one is even easier, but let me also do this. So this is how an inside pair look like. So AI is inside BI. And what if BI plus 1 was outside? Then we have a problem, because AI is under BI, and this was an incomparable pair. So BI plus 1 is actually inside this region. And this shows that BI to BI plus 1, we have a region inclusion, and this is a strict inclusion because these elements are different, and this also cannot cycle. Yes, so this proves that insides are also reversible. Yes, so this finishes the maybe the only proof which I showed with all the details, and which I will show. And now we will move to some more difficult stuff. But this idea with dividing pairs into types will stay with us, and leftmost, rightmost paths, and so on. Okay, so recall this table. I will show it a few more times. We already did this cell, and now we want to do this cell. So what is the setting? Cover planar. There exists 0, so unique minimal element, and we want to prove that dimension is bounded by this very nice function of a standard example. Okay. And recall this unfolding. So recall what are we doing? This was the general problem. So we reduced to blue and red, but we assume that there is no red. Yes. So this is what we're doing. We are doing like half of this general problem. Yes. Okay. So let's start. First of all, we want to repeat this trick with leftmost, rightmost path. But in planar cover graph setting, it's a little bit more subtle because okay, I have my 0, so my minimal element, unique minimal element. I have some x, some fixed element, and now say that I follow the leftmost path, I follow the rightmost, and they meet. This is fine. It was possible also in the diagram case, but they don't go further, but they return. Yes, they return. This is possible. Yes, this is still fine. It was not possible in diagram case because all edges went up, so I could not return. But here it's fine. Okay, and again they go for some time together, then they split, then they again go together, they split, and then maybe they again reverse. Yes, those arrows should help you understand which edge, which line goes in which direction. And okay, and maybe they reversed again. So this x might be buried very deep, very deep inside. Yes, but fortunately we still can define the leftmost path to x as this one. Yes, but now it's a little bit more complicated. Okay, we define the leftmost path, and in this analogously the rightmost path. So we can do the same trick with dividing our pairs into left, right, inside, outside. And it turns out that maybe it's a little bit more subtle, but again, left plus outside, right plus outside are okay, are reversible. So inside pairs are the hard ones, and now it's not that easy as in the previous proof. It's much harder. So I will give you some ideas how to cope with inside pairs. Having an inside pair, we define an address, and I will tell you in a moment what is this J and B. But first of all, note that there is a natural notion of depth of X. Yes, because here I return 1, so I go to a deep depth 1, then I return again, I go to depth 2, and I return again, I go to depth 3. So each time I say I say something about depth, I mean this notion of depth. Yes, and in the paper and in discussions it's called shadow depth because these things are called shadows, but I don't want to elaborate on this. Okay, so this JAB might be called the depth of a pair, is the first level, so first level in the sense which I discussed, such that A is not going along with B. So B is buried deeper, but A is not. Okay. Maybe it's going to be clearer on this picture. Yes. So we started somewhere from here and we follow those leftmost, rightmost paths and we go some deeper, but A stays. Yes, and B goes deeper. And B is just a block, so this is a block in which A is. Okay, so the next thing. So this was just a definition. This is an address of a pair. Next thing, we divide inside pairs into two sets by parity of this number JAB. Yes, so if it's odd, then it's in I in 1. If it's even, then it's in I in 0. Oh, and this is maybe a good place to remark the thing that this 2 here, this 2 is the same 2 as these 2 extensions, and this 2 here, so 2 times, is the same as this one. Yes, we divided into 2 parts, and this is this 2, and now we only are left with finding the standard example. Okay, so let's move on. We want to know how alternating cycles in this set look like. So we fix some strict alternating cycle, and now there is some work needed to show that address of each pair in the strict alternating cycle is constant, so it's equal to some fixed JB. This block B is terminal, meaning that this A is in the last block, so it's not in any previous, but in the last block, and it has a direct access to B in some sense. And some more properties, which I will try to illustrate on the picture. So let this be x naught. We can be buried very deeply, but we finally get to this block B, in which all the action happens, because we now know that all action happens in exactly one block with this cycle. Okay, next we draw all these which are in between this x here and this y here. So those are elements which are above x and below y. And we don't like these elements. So we can prove that not only the whole action happens in this block, but it happens in some phase here. So in one of these shapes which are adjacent to y. Yes, so the whole cycle is in this one phase. So in particular, we can reduce to our attention to this phase, and we can assume that in this phase there are no such green elements, no z's which goes through the middle. Yes, so let us zoom in to this green part. So now this whole thing is the green part. Yes, x naught, sorry, x prime. This x prime is this x prime now, and we have the things zoomed, and those dots, they really tell that this alternating cycle look like this. So there is many properties listed here, but maybe the picture is the best. So A's are sorted left to right, A's are hanging from x prime, B's are sorted left to right, they are hanging from y, and there are some comparabilities in between because this is a cycle, but I didn't draw them to not make this picture even more complex. And also note that A's can be taken to be the terminal point, so there is nothing later, and B's can be buried much deeper inside. Okay, so now is the most complicated part, which yeah, I just want to sell you some ideas and without details. So I hope it's not going to be very vague, but we take these pairs, which we know that they are hard, and we build an auxiliary directed graph, which we call h theta, on inside pairs in this hard set. How do we build this graph? We put a directed edge from AB to A prime B prime if we have one of two situations, and in one situation we call an edge strong, in the other situation we call an edge weak. Strong edge means that, okay, A is less than B prime, A prime is less than B, and the order is this one. So, for example, A could be here, A prime could be here, and B prime could be here, B could be here. Yes, so this arrow means an order in this strange ordering. Yes, so actually this is a two cycle. This is an alternating two cycle, which is nice. Okay, and the next, the weak edges are even more complicated, and it means that there exists such UV such that this is the case. But let's not go deeper. Now we divide our set of hard pairs into subsets by the longest path in h theta, starting by the length of the longest path starting in this pair AB in h theta. Yes, so we have a pair and we check how long is the longest path which starts. This is a directed graph, so starting makes sense. Okay, and now comes a few lemmas which are non-trivial, and there is some work to do, but I just want to state them. So it turns out that E theta M for a fixed M and theta is reversible. We have large dimensions, so there is not possible that there is very few of these sets. So it implies that there is a long path because some I theta M with a large M is non-empty, not reversible. Sorry, yes, is non-empty. Okay, next thing, if we have a long path, then we can eliminate weak edges. So long path means that we have a long path on the strong edges, only on strong edges. So we take this path and we replace each weak edge with a strong edge in some way, non-trivial again. And then I think which is much easier, strong edges are transitive. But these are two cycles, so transitivity of strong edges gives us that if we have a long path on strong edges, then we have a large standard example. And this is idea which stands behind this proof. Okay, and this is all what I wanted to say about this proof. Yes, so we can move on to the next one. Next outline. So we've done this, and the last outline which I want to show you is a planar case with no restrictions on minimality. Okay, so let's go. I will give you some basic ideas. I hope you remember unfoldings. So we're unfoldings. If we do unfolding once, then we have this blue bubble accessible from below. Yes, so there are these zigzag paths which go under each minimal element, meaning that this blue part is accessible from below. But if we work a little bit harder, so actually this is an idea which we borrowed from the paper by Jędrzej and Wichert, which shows a bound on dimension by hive in the same setting. If we work a little bit harder and we take 3 unfoldings instead of 1 unfoldings, then we can partition our poset into parallel problems, and each of these problems have the property that x naught is actually under each minimal element of this blue part. Yes, so from accessibility from below of this blue part to having a unique minimal element, we need some there is some work to be done, and most of this 128 comes from this reduction. Also, we can assume that x naught is itself accessible from below. Yes, so from x naught I can go with a zigzag path to some outer face, and this wasn't here. This is some new part. Okay, but yes, so we are now in a very nice setting of having this blue blob with a unique minimal element and these red elements hanging. Okay, by B I mean blue, by A I mean red. Now A and B are themselves accessible from below, and this is we can use this result as a black box. Yes, so dimension is bounded here, so we don't care. So we only focus about pairs which are between A and B. Yes, because it's possible that large dimension is in either A or B, but actually it's not possible because of this result. So only pairs which are the problem are between A and B. Okay, and now the next step is to exclude some easy pairs, some pairs which are considered by us to be easy. For example, we can take I1 to be AB such that A is above B. This is a diagram, so this is strange, yes, because if A is less than B in poset, then A is below B. And for this, to reverse such a set, we can take one linear extension which sort our elements by hive on a planar drawing. Yes, and so this is reversible actually. Then we do some other simple reductions, which I don't want to talk about, and we obtain some set I, which is a set of hard pairs, actually hard, yes. So we know that the whole dimension problem is really hidden here because each of this finite number, bounded number of subsets is reversible. Okay, and to cope with these hard pairs, we need to recall rightmost paths. So we take B, so the blue part, and we draw the tree of the rightmost paths. Yes, so we have this minimal element, and we can draw the tree of the rightmost paths. Okay, and one of these reductions was that A's which we consider can be considered more or less to be right of this tree. Yes, so in this area somewhere. Other reduction shows that if AB is hard, then the pair has guards. And by guards, I mean B prime, B double prime, such that they are enclosing B. So B prime is left of B and B is left of B prime, and A is comparable to both of them. It's not that hard to show that in this hard that pairs which do not satisfy this are easy. Okay, so the next step, as in the previous proof, was to investigate how alternating cycles look like. And we have a very good understanding how do they look like. First of all, if I assign B1 to the rightmost blue element in my cycle, then they are sorted. Yes, so we can prove that there is an order, so that this order on indices is the same as an order in the tree. Next thing is that when I start to draw some A's, so for example, this is A1, and as I said with these guards, it encloses B1 in its region, then I know that if I get the A2, two possibilities are, there are two possibilities. One of them is that A2 is neighboring, so it's next to A1, yes, as in this picture. And the other possibility is that A3, for example, A3 to A1, A2 is nested. So it contains previous elements in its interior of this region, which is given by guards. Yes, so this is some cycle, and we know that all cycles look in this way. Also, we know that this A5 has to be the nested case. Yes, so it has to enclose the whole thing, the last A in the cycle. I like to draw it in this way. Yes, so we have this tree which is now just a line, and we have either nested A's or neighboring A's. Yeah, yeah, probably this is not very clear, but I just want to say that we really understand how the cycles look in this reduced setting, and because we understand this, we know how to construct this directed graph again. Yes, and so we again construct an auxiliary directed graph on these hard pairs, and now we have an edge if, and here is a picture of some structure. So if this is the case, actually, and by this I mean that first of all, B prime is left of B. So we have this as in the picture. A prime is less than B. Yes, we know that A prime is incomparable with B prime. So that's why this is like this. And we don't know if A is less than B prime. So this is dotted because it might be or might not be, and this distinction is a distinction between strong and weak edge. So it's strong if I have a line here, and it's weak if I don't have a line here. Yes. And now I do almost the same. So IM is now the set of pairs such that the longest path starting at this pair has length m, but now we count only strong edges. So you can think that strong edges have weight weight 1, and weak edges have weight 0. And this is how we can count the length of a path now in this proof. And now the list of lemmas, which are not trivial and a lot of work to be done. So first of all, IM is reversible. Second, by the fact that the dimension is large, so if IM is reversible and dimension is large, it shows that there are two sets, so IM and IM plus something, and this something has to be large, and this is not reversible. Yes, so maybe I shouldn't put 2 as I should put that this is some large number. Yes, so I have two sets such that two sets of incomparable pairs such that if I take them together, then it's not reversible. So this means that I have a long path in this H, but also I have a strict alternating cycle, which shows that this union is not reversible, and this cycle is like spreaded very. So it has many elements in between beginning and end in some way, yes. And this structure, so this long path plus cycle gives really a large Kelly. And Kelly has large standard example, and this shows the assertion. Yes, so so this is an outline of this result, of the proof of this result. And now you may notice that both these proofs which I showed you are in a sense similar. And now I want to summarize these similarities. So steps in these top two hardest proofs in general are that first we exclude easy pairs. So we take I1, I2, and these are some set of pairs which are reversible. We reduce only to hard pairs. Now we try to understand how strict alternating cycles look like on hard pairs. So in one case it was this picture, in the other case it was this picture. And this gives us an information how to build this auxiliary directed graph on hard pairs. We showed that because of large dimension, this directed graph has some long path and maybe with some additional structure, like in the second proof. And we showed that this long path or a long path with additional structure induces a large standard example. Yes, so these are steps in general and some high-level description. So I hope maybe it's helpful to understand what's going on. And yes, so I discussed all results in this table which I want to discuss, and now the time which I have left, I want to show you some other problem, some related problem to the unboundedness of planar posets, but some other. And this problem is about drawings of cover planar or planar posets with standard examples. We know these two. Yes, this is Kelly, this is the wheel, and they are planar, cover planar with large standard examples. But are they optimal? So yes, our question is, are they optimal? I here put an arrows which case do they witness. So this one witnesses that in this case dimension is unbounded. This one witnesses that in this case dimension is unbounded. And as I said, the question is, are these pictures optimal? Are these drawings optimal? So what do I mean by optimal? This is a little bit philosophical statement. So to formalize this, I want to know if a standard example of a poset is bounded by some nice function of Kelly or wheel. Yes, so this is Kelly, this is wheel. And this is what I mean by a question of optimality of these drawings. Okay, and in this case, in this planar diagram case, by this proof I done a minute ago, we trivially obtain Kelly instead of standard examples. Yes, because at the end I didn't tell you that I obtain a standard example. I told you that I obtained Kelly. So this trivially gives what I wanted. Yes, standard example is not bounded by a function of Kelly. But this 128 is not nice, and maybe in general it's hard to reduce it, but maybe taking only this problem into consideration, it would be easier. So why not, for example, put 2 here and prove this? I believe that it should be much closer to 2 than to 128, and this would also show that it is more optimal. So this is some open question to improve this constant here. And now what about the other case? we proved that dimension is bounded by 2 times standard example number plus 2, and non-trivially from the proof, and this was done by myself and Tom Trotter this summer, we can replace the standard example with the wheel, so the largest wheel which this poset contains. Yes, and this would give us this. Yes, so you see that in both cases the proof goes, we take proof of this and improve it. Maybe it can be done much easier, and that would be great to do it much easier and not to go through these complicated proofs, but who knows. Okay, and one more corollary of this. It turns out that if I have cover planar poset with 0, then dimension is bounded by by tree width of the cover graph, some function of tree width of the cover graph. Yes, and so this was a question which motivated us to do this work because this was the original question, and this question makes sense because, for example, tree width of Kelly is bounded by 3, so in some sense, this result is optimal because I cannot, being in any of these two cases, I cannot obtain such result. Yes, but this is just by forcing a grid in this cover graph. Okay, but let me say a few words about proof of this one. So how do we do this? Recall this picture. This picture was a picture of of a strict alternating cycle in this cover planar with 0 case. Yes, this is the picture from this proof. But by the way in which we constructed a standard example, this can be also a picture of a standard example. Yes, so a standard example, if it is in such poset, then it's also in this green phase, which was in this bounded region, which was so we also can find standard example very locally. And this non-trivial work, which I mentioned here, is forcing this picture. So standard example is really of this. It looks like this, and by some analysis, we forced it to be this picture, and we know that that's it. Yes. So what's going on here? We have A sorted down there. We have B sorted up there. And we have some lines which go to these chains, which are the rightmost or leftmost paths to B's, and these blue paths has to be chosen quite carefully to be leftmost or rightmost, depending on which exactly we consider, and then it works. It all works. So let me just to finish up, let me show that this picture really contains the wheel. And also it turns out that it contains Kelly. So this wheel can be also replaced with Kelly, but this is not like surprising because the wheel contains Kelly. Okay, so I have this purple points here, and it turns out that if I have these purple points here in Kelly and this yellow, then it's yes. So I hope that you understand. Yes, these purples are these purples, these yellows are these yellows, and this is the same picture actually. If we forget about some transitive, so yeah, if we consider some transitive edges instead of covers. And in the case of wheel, it's a little bit more subtle. This is the purple chain, and this is the yellow chain, and then you can carefully check that this is exactly the same. Yes, so this picture is very nice because it captures a wheel and Kelly. Okay, and let me summarize the things which I told you about and the things which I didn't tell you about. So first of all, we have this table with an open problem of determining dim boundedness in cover planar case without restrictions. We have this table, which I told you about. So this is about drawing standard examples on the plane. Zero and planar cover we have bound by Will. Planar we have bound by Kelly. And also in general, Tom Trotter claimed to prove also this summer that that standard example is bounded by function of Kelly, but I'm not sure what this function is. So, and I think it's not very nice. So probably there is also some room for improvement. And the related problem, which I didn't mention before, so there is a notion which generalizes dimension, Boolean dimension, and part of this big question, so this big question about dim boundedness of planar posets is usually asked along with a question of boundedness of planar posets, of Boolean dimension of planar posets. So these two are just obvious corollaries from these two, because dimension is, Boolean dimension is bounded by dimension. This one is part of the same paper as this one. So in cover planar with 0, we have bound by 13, and these ones are open. We are currently working on this one, but we'll see if we can manage to do this. Okay, and these are some nice posets ideas, and this is all I wanted to say. Any questions?
Yeah.